A very good morning to all. I welcome all the participants to the day 6 session. I would like to take this opportunity to introduce today's resource person, Dr. Sreekanth, who has graciously accepted our invitation to join us today. He is working as a project manager for L&T Technology Services, Mysore. He has completed his BE from PES Mandya, MTech from SJCE Mysore, and PhD in Image Processing and Speech Signal Processing from the University of Mysore. He has secured second rank in MTech. He has a total of 12 speech signal processing, data structure, MATLAB, Python programming, and machine learning. We are honored to have you with us today, sir, to share your knowledge. Thank you.
Once again, good morning everyone. So, myself Sreekanth. I work as a program manager in the domain of embedded systems and platform software at L&T Technology Services, Mysore. Let me explain at the outset what we work in the area. How many of you are from E&CE? All of you are from E&CE? Faculties? Okay. So then what I speak will be relevant to all of you. So let me touch upon what is the difference between whatever the research we do at the, because I have experience of both academics as well as industry, right? So I know what's the gap, right? While doing the research, what we consider as an academician and what industry experts. So both are of very different entity. So at L&T we have different domains. So I am catering to the vertical part as transportation, right? So I'm working in the automotive audio domain. So we have medical, so those who are working in the area of artificial intelligence, right? So we have medical domain, and so where they develop applications or solutions for guided therapy or whatever it may be for the doctors, right? For example, if there is a tumor in certain region, so nowadays L&T has come up with a solution where you can guide the doctor to the area where the tumor is exactly so that they can operate, right? So that is one thing, and so there are many applications in medical. For example, the doctor will be wearing the gloves when he is doing surgery, right? So if he wants to see the screen, so then he was touching the screen with his gloves, and there will be smearing effects on the screen, right? So now, so each day doctors comes with the new requirements. So now if you just go in front of the screen and if you just do your gesture, right? What I'm telling is where all of you will do gesture-based something projects, right? But you would have not thought of real-time applications of that. Right? So now just if you go in front of the screen and if you put the gestures, so it will enlarge zoom, right? So and it will help the doctors accordingly. So this is in the medical domain. We have a 5G, right? And we have transportation. So similarly, we have many verticals. So we are horizontal, embedded is horizontal. We cater to all this vertical because vertical will get the project for us. Because they deal with the sales team. Sales team is the one who will be sitting in our abroad locations where they go in touch with customers They will sell our capabilities. They will not sell products because we are not a product-based company anymore. So they will sell our capabilities. For example, if you consider our team, they tell that we have a DSP team who can cater to all these needs. So that is the part of the sales team. That is how they get the project, and we are responsible for its delivery. Right? So this is the picture of at the outset how we work as an organization. Right? So coming to my area, so I work for one of the premier automotive audio customers. Right? So nowadays our solutions we can see on the Indian road. Previously, none of the Indian cars had our solutions. Right? So now we have our solutions. You can see our solution even on the Indian road. So I am responsible for all the DSP projects that happens in L&T. Right? So I am, as I mentioned, about the audio domain. So let me give, because I had planned for time frequency analysis. So Patil sir mentioned no maths, no technical. So just talk about what you are doing in an organization, right? So let me walk you through certain features that we work right, in the audio domain. So I think all of you would have experienced that nowadays, if you buy any car, right, its mechanical cost is just 50% or even less, right? So assume if you are buying a 20 lakhs worth car, so the mechanical cost is less than 10 lakhs. So the rest is going to the consumer electronics kind of stuff, right? It may be safety, security, or entertainment, right? So we work in the area of entertainment, right? So what do you mean by entertainment in any car system? Music system, right? Okay, so what we have in our current road condition is that, but I'll explain what are the other features we work for. Porsche is one of our premier customers, so I'll explain what are the solutions and that we have developed and what are the upcoming solutions we have for other variants of EV cars or something like that, right? So what is the input for car audio system? You just think of, right? How do you get audio to the car? Sorry? Okay. Pen drive? Bluetooth? Sorry? Aux cable? FM? Right? So there are RCD drive if it is if just the customer still wants CD drive, right? CD, pen drive, Bluetooth, aux, right? And what is one more? FM, right? So this may be your source of input coming into the car audio. So is that a stereo or what is that is coming in or the surrounding, right? So we get stereo contents, left and right, right? So, but customer comes with statement that I want surround effect inside the car. What is the meaning of surround effect? You would have heard of Dolby, right? Dolby Atmos or whatever. Right? So those are called as surround. So given the stereo content, we need to create what? The Dolby effect inside the car, right? So for you it is just speakers, for us it's a channels, front left, front right, back right, center, right? Surround, it depends. So nowadays cars comes with 12 speakers, 16 speakers, even up to 28 speakers, right? So now those are redundant. So they are trying to get 4D effects, 5D effects inside the car. Right? So if you can feel the sound coming from your footrest, right? Coming from your right. So those are the technology that we are working in. So given stereo inputs, we are trying to generate what do you call so many number of channel outputs. Right? So let me give at the outset how we are working on. Right? So assume the input comes in, which is stereo, which consists of left and right channels. Right? So in the audio, what is the difference between audio and speech? Any of you are doing research on speech signal processing or audio signal processing? Do you know the difference? Are there any difference between speech and audio signal processing? What is the difference? Both are non-stationary signals, right? And what is the difference?
Music.
Sorry?
Music.
Apart from vocal, you will get music, right? So that's the difference. So if you get 8 kilowatts of sampling frequency, it's enough in your speech processing because maximum is 4K that you can reach. Whereas in case of audio signal processing, we go up to 24K, so we need 48K sampling rate, right? So this this entire 24K bandwidth of signal can be divided into three parts. One is bass, mid-range, and treble, right? So any audio signal content can be divided into three, so which we do not do in speech. Right? Anything between 0 to 100 Hz, we call it as bass, right? What is bass frequency? Any of you heard of? What is bass? Anybody aware of music? Bass frequency. What is bass? Your resonant frequency, right, of your vocal cord. Right? Each one will have different bass frequencies. Right? And mid-range frequency are between greater than 100 to 4 kilohertz. Right? And we have treble part. So I will explain why I am explaining all this. Anything greater than 4 kilohertz, we call it as treble. So any audio signal can be broken down into three frequency regions of interest: bass, mid-range, and treble. So once we get this stereo, right? So we have something called as input EQ, right? EQs you are aware of, right? Equalizers. Nothing but your pool IR filters. Right? So if you have designed pool IR filters, so one thing you should consider is, assume if you are designing a 8th order filter, so what we will do? We will design a direct form to 8th order filter directly, right? So that is not the good design. So you should design a bipod filter. So bipod filter is nothing but a second order filter, right? So then you should cascade. Otherwise, your quantization noise effect will come into picture, and whatever the output you get may not be the same as what you are expecting, right? So if you are designing any filters, so design it as a second order bipod filters and then cascade. You know how to cascade and all those stuff. So input EQ is there. So this input EQ is nothing but equalizer, which is a polar filter, right? So this we have designed in such a way that if the input is FM, right, a separate set of coefficients are applied for FM inputs, and separate set of coefficients are applied for aux input, right? Or your pen drive, you'll be playing MP3, right? MP3 is nothing but a compressed format, right? So we use a different set of coefficients for those MP3. We have some feature called as compressed audio enhancement as well. If you are playing MP3 files, which is in a compressed format, we have compressed audio enhancement, which is test the frequency region and then apply the gain, right, or the coefficients. So what I wanted to tell is, I am not giving the entire audio chain algorithm. So whatever the region of interest that falls within the domain of E&CE, and in our audio chain, I am explaining that. So this is we have designed different coefficients for different format of inputs. So that is the first step it goes through. Next, so once it comes out of this, we divide this into three frequency bands. What are those? Bass, mid-range, and treble. So this is how any amplifiers or any audio DSP solutions will work. Take it of example as Harman or Bose or whatever it may be, right? So the fundamental principles remain the same, right? Otherwise, you cannot get the Dolby effect what you are hearing in your inside the car or in the theater. So bass, as I mentioned, it is 0 to 100 Hz. So why I have taken this example is, see what I said, the sampling rate is 48,000, right? Bass frequency is, what is the max bass frequency? 100. What is the max mid-range? 4K, right? Treble is anything greater than 4K, up to 24K, right? So now, the constraint what we face in our day-to-day life is, right, the customer comes. So earlier we were working on analog devices, DSP processors, right? So the trend doesn't remain the same, right? Some other customer comes and says, we want your solution on Qualcomm Snapdragon, right? And somebody comes and says, we want your solution on Samsung, right? TI Jacinto, right? So the platform keeps on varying. So what is the constraint we face is memory and MIPS. MIPS is nothing but million instructions per second. How many your code should be compact enough to run entire algorithm on that chip, right? Otherwise, you'll run into issues, right? Your pop noise, audio will be distorted. So we should develop, or we should optimize our algorithm such that it fits on whatever the platform they ask for. this is one reason why I have got this. Right? So base is 100 hertz. So according to your Nyquist criteria, what is that is max required for that? Right? Anything greater than 200, right? For 4K, anything greater than 8 kilohertz. Right? Otherwise, what will happen? Overlapping. What is the meaning of overlapping? Textbook you are seeing triangular waves overlapping one over the other, right? So let us take, since there are many students will, from the student perspective, will take an example. So assume I have a signal, right, of which is consisting of two frequencies. Assume one is 50 hertz and the other is 100 hertz. Now let us take 400 and 200. Okay. So if I take the FFT, what you will get? Assume I have taken 1 hertz resolution of, number of FFT points I consider such that I get 1 hertz peak resolution. So what is that you see in the frequency domain? Anybody teaching DSP here?
2 peaks.
2 peaks, very good. One at?
Yeah.
One at 200 and the other at 400. So I am teaching what is aliasing in practical, right? So if you see certain waveform, you should be able to judge that I am getting this because I have not selected the proper sampling frequency. So 200 and 400 are the peaks that you expect for this signal. Right? Assume you expect this peak only if you have selected your sampling frequency greater than 800. Right? So assume I am not a DSP engineer, I have selected sampling frequency as 700. Right? So what is the case? So this is an example of aliasing. Right? So now what are the frequency contents in my Fourier domain? Right? For 200, 700 is more than enough, right? So it doesn't undergo any aliasing. Right? I will get 200 as it is. So what about 400 component? 400 takes the appearances. So if you take 700 as a sampling frequency, your folding frequency will be 350, right? So reflect 400 over 350, you'll get what? You'll get what? 300, right? So this is termed as aliasing. One frequency taking the appearance of other frequency. What is that one frequency? 400 hertz. Now after sampling, it is taking the appearance as 300 hertz. So this is called as aliasing. Why? Because here the base mid-range interval, what I spoke, we do multi-rate DSP now, right? We do not, we will not go with the same sampling rate because 100 hertz, 200 hertz is enough. Right? It means 200 samples is enough, processing 200 samples. But if you use the original sampling rate, you will be processing at 48 samples, which is a waste, right, of computation. So now, what we do? Forget about base, for the mid-range, 8 kilohertz is more than enough, right? So now we will try to operate at Fs by 4, right? So what is Fs by 4 now? Assuming 48K as your sampling frequency. So what is Fs by 4? Is that more than enough? Right? So that's why we divided our spectral content into base, mid-range and treble, right? So where we can optimize, how we can optimize our algorithm. Right? So now you can see that instead of operating at 40K, we operate at 12K. So there is two decimated rate processing happening, one at base and mid-range, and one full rate processing happening, which is called as treble part, right? So ultimately, what we do is there are some proprietary mixing equations, right? So given two channel content of base, mid-range and treble, for example, I will tell. So once you convert that into Fourier domain, you will get certain coefficients, right? So we may do front left plus 0.5 times of front right, and you can center, you can derive it as front left, front right divided by 2, whatever. So these are the equations which we derive, and once these are mixed, you can reconstruct your signal back, but ensure that while reconstructing after your upsampling and all the stuff, all the samples should get aligned from base, mid-range and treble. Even one sample misalignment will become a top noise. Right? So we ensure that all gets aligned. We should calculate the delay even in terms of one sample, right? Because base output comes fast. It is only 200 samples, right? What we need to do, we need to add a delay block here. We should delay number of samples in such a way that it gets aligned with this mid-range and treble when we add. Right? So these are the algorithm constraints I'm telling, right? So you should, based on the processor, you should calculate the delay, right? Based on your clock cycle, how many clock cycles it takes. So based on that, we add all those contents. Now you feel from 2 channel to whatever it may be, 12 channel or 16 channels. Right? You can route each upmixed equation to different channels. Right? So surround content, referral, mid-range. So that we have felt here. Right? So I played some Kannada songs. How we can hear from each and every channel, we can feel. So these are the constraints what we get in our day-to-day algorithm activities. Right? So how to optimize and other stuff. So this is about entertainment path, right? So this is not complete. This is a Dolby feature. So once this is there and this output goes through some post-prod, we have limiters of clippers, right? So what will happen is, if all the speakers are playing at certain voltage, right, assume greater than 2 volts, right? If 12 channels are playing at 2 volts, there is a possibility of blowing off, speakers gets blown off, right? So we have a limiter, will check whether all the channels are being played at the same voltage or even less, right? We will consider the threshold as 8 number of channels, for example, one application. If more than 8 number of channels are playing at so and so voltage, we will bring that volume down, even though you are increased, right? You can feel the volume coming down. Right? And okay, so we'll go to the new one. So this is entertainment part I explained. So what are the other features that we work on? So we have something called as engine harmonics cancellations, right? So as I mentioned, these are the solutions for high-end cars, for example, Porsche. So they want noise-free cabin, right? They don't want any noise inside the cabin, right? So we have features called as engine harmonic cancellation, road noise cancellation, right? So friction of the tire with the road will also come inside the cabin, right? So if you sit inside the car with these solutions, you do not feel any external sounds. Right? So engine harmonic cancellation, what we do is, for every RPM, we would have stored the engine noise already. Right? So it's a lookup table approach. So assume this is for RPM of 100. Right? So even with cars with gear, we consider the gear position, right? And the speed, all those stuff. So 200, assume this is how the engine harmonics looks like. So what happens? You want cabin with which is void of engine noise. Right? What we'll do is we'll read the real-time parameters from the car. Right? What is the RPM and all the stuff. We pick the corresponding anti-noise. Right? These are the lookup table corresponding to the anti-noise of the engine harmonics. Right? What is anti-noise? Assume if this is your engine harmonic, anti-noise would be, right? So the entire process should happen in real time. There should not be a delay which is greater than 1 milliseconds, right? So assume there is a slight delay because of which you get something like this, right? Which is better. So this is the one which is void of noise, right? So generate the anti-noise. If you want to do some experiments, take a speaker, right? Play one song and you generate the anti-signal of that, play through that speaker, you will not hear anything. Right? Even though both the speakers, the outputs are being played at full volume, you will not hear anything. Right? So this is how the engine harmonic cancellation is done. So similarly, we have road noise cancellation, which is to remove the road noise due to the friction of the tire with the road, right? So those noise also you can hear in your normal cars. If you close all the windows, you can hear all this type of noise, engine noise, right? Road noise, everything. So these are the other features we work on. So all these are based on adaptive filtering now, right? So one input will go through the primary input of the adaptive filter, the anti-noise will go through the secondary input, and you know how the filter gets adapted and all those stuff, right? So next one is engine harmonic enhancements, right? So one requirement is we don't want engine harmonic noise. One requirement is we need more engine noise, right? So you would have seen sports cars, right? So if you want to get the sports car effect based on your acceleration, even though your engine is not generating such harmonics, we artificially inject the harmonics, right? So whatever the sound you hear from the race cars, those are not from the engine, right? So those may be because of modification in the silencer or because of this algorithm sitting inside the car, engine harmonic enhancement. I think you know EV cars are the trend now, right? So when EV car passes nearby, you don't hear any sounds, right? So nowadays automotive standards are coming up with E&CE as a mandatory, right? So we incorporate those solutions into the EV cars so that when EV cars passes by, you can hear some sound, right? Which is not the engine sound because there is no engine in EV car, right? We artificially generate the engine sound for those cars. I think that becomes a mandatory in the coming days, right? So this is the other feature we work on, and you would have heard of chimes, right? So I have designed this state machine for tigers, right? So what is chimes? Chimes means when you are not wearing the seat belt, you will get one tone, right? When you insert your car key, you will get different tone, right? When the doors are open, you will get different tone. Parking rare objects, you will get different tone, right? So it looks very simple. What is there in playing the tone? But the pain is once you design state machine, you will get to know, because as soon as you wear your seat belt, the tone should stop, right? And assume some baby is sitting in the left side of the seat, right? So assume he is not wearing the seat belt, right? So it will stand up again. Suddenly the baby will stand up, right? The beep should stop, right? The input from the sensor it should read, right? So state machine is designed in such a way that it will cater to all these needs, right? Whether it's parking or seat belt or the doors open, all those stuff. And we have one more feature where you know that we have a sunroof now, right? Sunroof or moonroof or whatever it may be. You are playing some audio inside, right? And you want to open the sunroof, right? Once you open, what happens? Surrounding noise will enter, right? So we have an algorithm which will measure that noise and enhance your audio in such a way that you don't feel that noise. Right? So it will automatically recognize the mean value of the noise, and then we update the volume parameters or whatever gain parameters or whatever will such that your audio quality remains the same inside the car. Right? So these are the gist of features that we work on our day-to-day activities. Right? As I mentioned, the pain what we face is, for example, our FIR filter will take assume 500 pips. Right? Assume customer gives a hardware and he says that you should fit this in within 300 pips. Right? The pain is you should optimize it by 200. How do you do it? Because it's already optimized code which you are working on one platform. Right? You need to further optimize because the customer is giving only that much space. He is not giving the full space because nowadays ADAS features are coming, right? So previously we were selling our things as along with hardware. Now people are asking for software as a solution, right? So previously we were giving our speakers only and everything was going in as a entire integrated unit. So now because of ADAS features, so they will tell that we are going with Qualcomm processor because ADAS features are good there, right? I mean, the processor is good to accommodate ADAS features. What it may be your 360-degree camera or whatever it may be, right? So previously we are selling it as a unit only of audio signal processing. Now your image processing, artificial intelligence, everything is switching in. So we need to integrate our solution to there, right? So it's now software as a solution. So when I talk about software as a solution, please remind me, I will show you how we can generate a C code from Simulink models, right? Because many of your faculties here, it may be hard to code in the C coding, right? I will show you how you can generate the C code by just pulling the Simulink blocks available. You can design your system, right? Based on the target, you can generate the C code, right? So please remind me, I will show that. So these are the features. So that one pain is when the platform changes, right? So it is difficult, it's a pain for optimization, right? So that's why what I was telling is, so when you are working on your research part, don't think of only innovative solutions, right? You have FFT, right? Check whether you can optimize further, right? What is FFT? It's the fast way of implementing DFT. Right? So we know that how many additions, multiplication it takes. Is there a way to reduce that still? Right? Because FI filtering, as I mentioned, decimation, interpolation, we use polyphase filters because regular filters will occupy more. Right? What is polyphase filter does? It will avoid unnecessary multiplications with zeros, right? Which is not required. So, while considering any research problem, don't consider only from the invention point of view. So, take existing solutions, check whether you can optimize. Right? So that's what my request is, because I will tell. So this is the question I asked for. I have one of my team member from who has done a PhD in IIT, right? So what they have done is, even though he has worked on wavelet transforms, artificial intelligence, and all those stuff, everything he has done in offline, right? So offline means what you will do, you will take entire length of the signal, take filter, convolve, you get the result, right? But the same algorithm what he has developed offline will never work in real time, right? So what do I mean by real time, right? So my board will be like this. So it will be assume 32 sample buffer, right? Input buffer. So what do you mean by this? From the analog to digital converter, it can hold only 32 samples, not more than that, right? And then your algorithm. And then again output buffer is 32 samples, right? Input buffer and output buffer, right? So now I will ask some simple, I asked the same question to him, he could not answer, right? So assume 32 samples, my ADC, assume it will send some sample by sample, right? How it works? Once 32 samples are filled, we have something called as peak pump buffers, right? 2 buffers operating at a time. I mean, once this buffer is filled, next inputs will go to the pump buffer because you need time to process the input samples and send it to output, right? So once 32 samples are filled, it will trigger an interrupt. So once the interrupt is triggered, the algorithm will read the samples and it will do whatever it wants, filtering or FFT, whatever it can. And then it gives the output, it will send the output to output buffer. So the other buffer will be filling at that point, and once other buffers are filled, again the interrupt is raised, right? And the algorithm will go. So this is how it happens. So my question to him was, he has done very good publications and all those stuff, even IEEE publications. So I asked him this simple question. See, I have 32 sample input coming in, right? And I have a 4th order filter. Right? How do you process this data? Your algorithm has capability to take 32 samples and provide 32 output. Right? So you have 32 samples. Your filter order is what? 4. Right? So as per your basic convolution equation, it is 32 plus 4 minus 1. What is the output? What is the output? 35. You can send only 32 samples. What you will do with the rest 3? You will waste those samples, right? So this is where we should know about states, right? What you write in your theory, y of n minus 1, y of n minus 2, right? All these are states, right? So we should save those 3 states, right? What is 4th order filter means? It depends on previous. What is the meaning of order? 2nd order filter means what? You see y of n minus 1, y of n minus 2, right? What is 3rd order? Y of n minus 1, y of n minus 2, n minus 3. If it is IIR or it is IR depends on both x and y. If it is an FIR, it depends only on x of n minus 3, right? So it means the states. Based on the order of the filter, you should save these states because when you implement next time y of 0, it depends on these 3, right? So all these real-time constraint needs to be considered. Do not, while you are processing, while you are developing any algorithm, do not develop it from the point of non-real time, right? So try to develop a real-time algorithms which works, which divides your signal into frames, right? Your frame size you can take 32, 64, whatever it is. Just if I reduce based on the frame size, for example, assume analog devices comes with a buffer size of 32. Assume Qualcomm comes with a buffer size of 64. In my algorithm, if I just change it to 64, it will work, right? If I change the frame size parameter to 64, my algorithm will work, but your offline algorithms will not work, right? So when you are trying to implement any algorithms, so please try to implement considering the real-time constraints, right? So buffer size varies from platform to platform. So based on that, you need to write your algorithms. Right? So now, as I mentioned, let me show you how to use. I heard that your organization has MATLAB licenses, right?
Yes.
So how you can make use of the license, I can show. Basic Simulink or you have packages, image processing, DSP, everything. Embedded product is there. So I will take a very basic example, right? You can design any models. So why I am telling is nowadays there is AI package as well, right? So input, drag and drop. For example, if you want to write, if you want to analyze input signal in Fourier domain or time frequency wavelet STFP, so drag and drop that block, right? And just generate the code. So take whatever the SDK you have, right? So compile that, cross compile that, and you'll be able to flash that code on your platform and be able to check the response. I am suggesting this is instead of just doing the offline simulation based algorithms, because there is a lot of difference between simulation and real time. Whatever that works in simulation is not the same when you put your code on the board, right? Because we are using pointers and all those stuff, right? So if you are not clear the pointers, right, how it crashes, we cannot expect, and then we need to debug all those stuff. So this is my algorithm. So I want two inputs, right? Whether it be positive or negative, I need to add those, right? And I should give the output. So I have considered a very basic example. Okay. So once that is done, you can go to model settings. laptop, I don't have license, right? So I could have showed in my customer laptop what are the different platforms it's already exist. I think you can generate code even for your Raspberry Pi. So can you see here hardware implementation, right? It has for hardware board, for which hardware board you want to generate the code, right? So even it has so many things, right? So why I'm telling this, when you're giving assignments, please give assignments because the boards are, you can get Arduino board even for 500 rupees, right? So let them implement it because you are not giving a big solutions, right? Assume if they want to do a 50, let them do here and show that. Right? So Arduino, I think it's just 500. So these are the different boards. So please check in your license what all hardware support you have, and check the cost of the board. Raspberry Pi even comes for 500. Right? So check for boards that student can afford, right? And then so once you select the target, say I will select the target as Arduino Uno, for example. Okay. So it will ask for other features. So sometimes how the byte search code may be little and linear we can get. So you need to do post processing if you are not aligning it properly. So once you select that, go to code generation. You should select ERT.ELC here, right? And then interface. See, this is the one I told, code replacement libraries, right? So assume you are generic F50 code. Generic F50 code means that code generated out of Simulink block, right? It may be inefficient. So there are something called as code replacement libraries. For example, Qualcomm will provide its own library for FIR, right? You need to integrate that here, and here you should select it as Qualcomm library, right? Or Samsung library. Right? I mean, if you are going for a higher end thing. Otherwise, since your solutions, your generic code will do if you are doing this FIR filtering, IR filtering, whatever you're doing, right? For that, these libraries are not required. So that's what I was telling. How we reduce from 500 to 300 is we'll go to the Qualcomm specific FIR filters, we'll implement, we'll test for our requirements. So then we replace that here. So once that is selected, you apply. Okay. Right. So control is the shortcut for generating the code and building the model. You cannot generate the code in the installation folder, MATLAB installation. So how we do is we have our own set of algorithms already existing, right? So once you do that, code gets generated, right? So once the generated code is already there, you know how to compile it, right? So even any, Arduino comes with its own SDK, right? So paste your code there, right? And invoke the code and build the code, right? And then flash it out to the hardware and check you have a reference vectors in your Simulink. Right? There are 3 types of testing. One we call it as mill. Mill means modeling loop. So I just made the model, right. So how to test that model? Modeling loop is input. I will give the first as positive input, the second input as negative input. Check whether it is working fine, right? So give both 0. So you should check for all boundary conditions, right? So that is how, because testing is a big area in testing. Right? So whatever the development time, it may be 32%. Testing takes 28%. That is the weightage we give. I mean, while putting the effort estimation, budgeting. So we'll say that assuming 300 days is the man hours we require for completion of this project, of which 32% weightage is given to the development and 28% to the testing. So it's like they are almost parallel, because if you are not doing good testing, even though you are a good developer, so the mistake may happen because it's a human error, right? And if you could not test, there is one example. So touchscreen we developed, right? And with the other team, how the good tester will differ, right? So how they will do? They will just do 4 quadrants. They will put pressure on each quadrant and they will check it's working, right? So one of my colleagues, what he did is he again subdivided that quadrants into 4, right? And he found that in one of the quadrants it's not working, right? So that is how the testing is very critical. Right? So it's rather than development, it's the testing, because once it goes to the field, it's a bad remark on the developer or the tester, right, or the organization itself who has provided the product. And we give some warranty time as well also, right, like 60 days, 90 days after the delivery. And if you could not fix within that, then we may have to face the penalty as well from the customers. Right? So all those are the agreements. So that's why testing is what I wanted to bring out is testing is also a major domain in case of if you are doing any embedded related projects. Right? So once you do this, code gets generated. You need to cross compile using your SDK and then flash it and check it. Right? I think you can give these kind of small assignments to the students. I mean, assume if you are doing a big project, right? Break down into modules. So give it to each student and then we can integrate. So I mean, whatever the offline solutions you are doing, it becomes a real-time solution is what I'm telling. If you do it on the board. So this is one part I wanted to help. And the other one is, so assume previously we are working with sampling rate of 44K. Right? Now the customer comes and he says that I want your algorithm to work at 48K. Right? So again, it's a painful process, because if you change the sampling rate, then what I said, the delay of what I have calculated, it would have taken years together. Right? That will all go in waste. How this multi-rate DSP will help is, we had this Dolby features all, even now we are working at 44.1K. So even the customer comes with 48K, what they want? They want 48K input, 48K output. And they don't bother how we do inside, right? Internal of the algorithms, they are not bothered. So what we did is, time to market is also less. Assume if they give 2 years, right? And assume you are developed your legacy algorithms taking 5 years, 6 years. Right? So those are the painful time, and after it starts giving a fruitful results, right? So development period will take more time. So what are the projects we are now working? So that will go into delivery in 2028 or something like that. It is not going to deliver tomorrow, right? That's how industry works. It thinks 4 years or 5 years from now on how it goes. So what we did is, since customer requested, we did change our algorithm to work at 48K. Right? We had our algorithm working at 44K only. What we did is, once we got the input, we upsampled it. We downsampled it to 44.1K. We fed it into our algorithm, right? And once we got the output, we upsampled again to 48K and we gave it. Right? So otherwise, you cannot change your legacy algorithms for one customer, right? Which will take years together and which will not be profitable business solution. This is how we work. So once we tell multi-rate mix, so you should be thorough in your basics, right, of designing. As I mentioned, once you decimate your sample, it is nothing but you are removing one sample or increasing one sample. It has after effects in frequency domain. It may become an aliasing component or a image component. Right? We should design filters correspondingly so that to remove all those things. So I mean these are the challenges I'm telling that which in our day-to-day life and how do we react, right? So we cannot deny customer because they are our bread and butter, right? So we cannot tell we cannot work for 48K, we work for 44K. So I mean if you are, I mean when it comes to my domain, so being strong in DSP with fundamentals will definitely help. If there are any questions, I think the floor is open for your questions.
Any questions?
Any questions that you want to know, you have, or you want to know? Yes, please.
So what makes the difference in audio system like the Dolby Atmos and the Dolby Surround? What they use?
See, as I mentioned again, it's for example, I should not tell because it's a business thing, but I will tell. So as I mentioned, you are a customer. You tell that I want Dolby effect, but I will give only this space, right? What we will do? What we can do? Assume we cannot optimize. What else we can do? Right? What we do is assume if you are using 500 amplifier filter, we will bring it down to 300, right? That is the only solution. And whatever the audio quality you will get may not be good, but you are satisfied that you got the solution within that. Right? But audio quality, what you get when you use 500 tab filter is not the same when you use 300 tab filter. But you can fit it that in your requirement, right? So it's that. So as you asked, rightly asked, so we have different things. So 5.1 is one, right? 7.1, even we have 9.1 now. So all this is the one, I mean, the number of surround speakers are more, that is how it matters.
But dividing this into three bands, bass and mid and combining all those things and due to that overlap of filters, is there any degradation of
Overlapping of filter means?
we need filters to divide the three bands. There is some overlap between the filters.
Okay, so
what frequency response?
Correct. So what is his question is, we are not designing any hard filters, hard cutoff filters. He's telling, you are telling 0 to 100 is one frequency, right? 100 to 4K is the mid range, right? You may not get 0 to 100 exactly, it may go up to 120, right? And the mid range can go from, instead of 100, it may start from 90 to 4100, right? So when we take FFT, I told you, right? So we have mixed in the domain of FFT, right? So once you take the FFT, we'll deal at the resolution of some 200 Hz, right? So you know this mid range would have picked 100 to 120, right? So you know where to start your beam in that case, right? So that will address your issue. He's telling that transition bridge will be there, how do you address that, right? So once you go to the FFT domain, right? So assume 20 Hz as creep deep, so which corresponds to first beam. I can do that too, right? I can consider in only one, not in all. Any other questions?
So we need some easier resources for it to strengthen them in the DSP fundamentals.
Okay. Because I'm the only resource available now. Let's see how we can do. So, but the thing is, you should all be strong in C programming, right? Because even though Simulink is there, you generate the C code, and if there is some error and if you do not know how to debug, then it will be difficult. Right? Embedded C you should be very strong, right? Looking at going to the, when debugging, you know, right? I think I'm not sure how many of you are aware of CCS or BDSP, the tools available for debugging. So once you build, you can load your project there. You can start debugging by keeping the pointers, right? I mean, you can go to that address and check whether the address is getting updated with the correct values. You can do all those. Samples will be coming in, filtering, and you can do those things manually as well and check whether the outputs are correct or not, where the things are going wrong. So that is how we fix it on the hardware.
Sir, you talked about converting the model into a code. Is it possible to convert back the code to a model?
No. What is the need? Reverse engineering. We have not said I will not do that. Okay. So I think so if you go through these concepts, so you can apply these concepts, all these DSP concepts remains the same, right? Either you can do time domain processing or frequency domain processing. Right? Nowadays people are going with artificial intelligence even for DSP, right? But the solution is costly when compared to the traditional DSP. So that's why traditional DSP is still alive. Right? How do you cancel this engine noise? You need to train each and every sample of the noise. Right? How much you will train? Right? Whether it will respond so fast like our traditional algorithms. Because we process using Windows, right? So your Windows size assume 32 samples every day. So it's well within the real time. Right? So you can process in time domain or in frequency domain. Right? Well, let us, since students are there. So what is the disadvantage of time domain processing? Can you get it to the market? So what is there? So assume I get some translation from lines. Right? So this is a time domain signal. What is the disadvantage with respect to this?
Continuous value rate change.
What is that you are missing here? You know, at this time information, this is the amplitude. What is that you are missing? So assume this is the audio recorded from some equipment where it tells whether the patient is audible to certain frequency range or not. Right? They will test, right? What is the range, audible range? 20 to 20 kilohertz. They will throw the frequencies, tone, and they will check whether they are able to hear it or not. Right? So assume the response is this. From this response, can you record to what frequency range the person is not audible? No, right? What is the disadvantage of time domain? You cannot localize frequency in it. You can localize only time. So assume if I apply FFT for this, or DFT, whatever it may be, and assume I get something like this. Right? So it gives some information now. So your time domain signal got transformed into frequency domain. Right? And now you have certain information. What is that information? It clearly says that the person is not audible in the frequency range of 3 to 6 kilohertz. So that is how your hearing aids are designed, filter banks. Right? So now you operate only on those filter banks which falls in this frequency range. Do not touch others. Right? Only those filter banks which takes care of these 3 to 6 kilohertz increase the gain. Right? So that is what is programmed inside the hearing aid chip. It reads to what frequency range they are not audible, and then it will adjust the gain. Right? So when it comes to adjusting the gain, so I forgot to mention that inside the car you just increase the volume. I'm telling the DSP thing there. Just increasing the volume means. So assume you are at 2 volts. Right? If you increase the volume, it will go to 3 volts. Right? But the DSP inside here is, it will not happen instantly. Right? It will take some 10 milliseconds or 30 milliseconds, which human ear is not able to recognize that. Right? So it will take some slope to ramp up, right? Which is 30 milliseconds. So I mean, these are the basics. Right? Just increasing the volume will not increase. So we will calculate the number of frames required to reach that gain, right? From 2 volts to 3 volts. The target gain is increasing by 1 volt. How many number of frames? I mean, the gain will not directly go to 2 to 3. So 2.01, 05, 07. Right? It will go in steps. Right? The steps is defined by that slope. Right? That slope again depends on what is the time you are giving. So if you are considering real time, so 20 milliseconds you will give. Right? Within 20 milliseconds it will ramp up. Right? So this is frequency domain. So what is the disadvantage in frequency domain again? So frequency localization is there but not time, right? What is the meaning that? So assume some earthquake happens, right? Richter map will say that, Richter scale will say that the impact is 7, when? And you need both, right? So we need time and as well as what? The frequency, right? At what time, what is the frequency? So for that we need to go for short time Fourier transform or wavelet transform. Only difference is short time Fourier transform, your resolution is fixed. Either you can get good time resolution and bad frequency resolution, or vice versa. You cannot get both good, right? So if you want both good, then you should go for wavelet transforms, right? So that's what I'm telling. So you can use all these concepts both in your audio or in speech processing, right? Speech processing you can use for speech analysis, picture extraction, speech recognition, speech synthesis, right? Speaker identification. So you can just start your speaker recognition just using FFT, right? For each speaker, extract some FFT coefficients, map it. Right? You can learn both DSP and artificial intelligence. Train those coefficients and tell that. So you can do it for your attendance system in your class. Please collect data of all of your friends, right? Extract the FFT coefficients, some 256 coefficients, and then try it, right? And then when the teacher calls, if the student responds yes, please map whether it is mapping to that particular student. And so these are the innovative projects you can think of, right? Speaker recognition. If speaker recognition was there at that time, the entire Ramayana would have not happened, right? Sita misrecognized the voice of Ravana, right? So if there is a speaker recognition system, entire Ramayana would have not happened. So you can avoid proxy attendance system and all those stuff, right? So just start a small project. So this is how you learn the technology. Take some 15-20 students, right, who are like-minded, and then start project. Collect the FFT coefficients, train it and check whether it's working or not. Efficiency may be 70%, and then try what else you can do. You'll come to know that FFT coefficients are not good. You have to go with exceptional coefficients, MFCC coefficients, right, all those stuff. So start with these kind of projects. Any project you think of in real time. Okay. Any other questions? Let me know if you want to know any other, pertaining to the area of DSP, nothing else, or about how the things happen in the industry. If you have any questions, please ask. Okay, thank you very much.
Thank you, sir, for your valuable insights and engaging the session regarding speech enhancements in automotive electronics, real-time embedded systems. Now, I would like to request Dr. Nagaraja Viji, Associate Professor, Department of E&CE, to hand over the token of appreciation to Dr. Sreekanth T, Project Manager, Automotive Domain, L&T Technology Services, Mysore. Your knowledge and expertise helped us a lot. Thank you, sir. And I thank all the participants for attending 6 days FTP.